In this exercise, we study the set consisting of all functions from R to itself. By convention, we use the symbol R to the power of R to denote this set of functions. Now, we define a binary relation on this set of functions. We're given arbitrary two functions, f and g, both from R to R. We say f is related to g if and only if there exists a closed interval ab, out of which fx minus gx is always equal to 0. As you can see, for f to be related to g, they don't need to be the same function. Rather, their values can differ from one to another within this closed interval. Naturally, the choice of such a closed interval should typically depend on the function f as well as the function g. It could be a very short interval, it could be a very long interval. Somehow, our interest in studying a pair of functions under such a relation is often related to the asymptotic behavior of a function. No matter how large this interval is, it will not impact the asymptotic behavior of our function. For example, let us say a function f is related to a function g. If the function f has a finite limit as x goes to positive infinity, then we know that g should have the same limit as x goes to positive infinity. After all, such a limit is an asymptotic behavior of our functions and should not depend on its behavior in any closed interval. Now that we have developed some motivation, let us proceed to prove that this binary relation is indeed an equivalence relation. As always, we start from the reflexivity. Let f be an arbitrary function from R to itself. Then clearly, fx minus fx will always be 0 regardless of the value of a real number x. Since this difference is constantly 0, it should still be 0 on the complement of any closed interval. And here we have completely the freedom to choose whatever a closed interval. It will always serve our needs. For instance, we can simply choose the closed interval 0, 1. Since fx minus fx is always equal to 0 in the complement of this interval 0, 1, we conclude that f is always related to itself. This justifies the reflexivity. Next, for the symmetry, assume that we're given two arbitrary functions from R to R, namely f and g, such that f is related to g. Then, by definition of our binary relation, we know that there exists some closed interval ab, such that fx minus gx always vanishes in the complement of ab in R. But notice that fx minus gx is equal to 0 means precisely that gx minus fx is equal to 0. In other words, gx minus fx is equal to 0 in the complement of the same interval ab. This means g is related to f, and we have proved the symmetry. Finally, for the transitivity, given three arbitrary functions f, g, and h, where f is related to g and g is related to h, then by definition, we know that we can find two closed intervals, namely a1, b1, and a2, b2, such that fx minus gx is equal to 0 in the complement of the first interval, and gx minus hx is equal to 0 in the complement of the second interval. Now, the key observation is that we can always construct some greater closed interval containing both a1, b1 and a2, b2. To this end, let us take a3 to be the minimum of a1 and a2. Meanwhile, let us take b3 to be the maximum of b1 and b2. Now, since f and g agree with each other out of a1, b1, and a1, b1 is a subset of a3, b3, we see that f and g must agree with each other out of a3, b3. Similarly, g and h must also agree with each other out of a3, b3. Combining these two together, we conclude that fx and hx must be identical in the complement of a3, b3 in R. In other words, f is related to h. This proves the transitivity. Now, since this binary relation is reflexive, symmetric, and transitive at the same time, it is an equivalence relation.